Okay, hi everyone. So this video is to go over page 6 of Midterm 2. This is for Chem 3A, which is Organic Structures and Reactivity. Said that so many times I can't even remember if that's actually what it's called. But it's for UC Berkeley. This is fall 2019. It was taught by MaryAnn Robak this semester. So here we go. So this page of the midterm is just like quiz 5 for this class, which is, as you said, quiz 5 again. And so we are deciding the configuration label for each one of the indicated sites. If it's none, that means it's not a stereocenter, so we also have to look for that. If it's E or Z, that's when it's an alkene, so that's the only place where E and Z can come into play, and R and S is for stereocenters. Okay. With that are making 4 different bonds to 4 different groups. Okay, so looking at the first problem, we're looking at this carbon right here, and it has an implied hydrogen. It's going to be right behind that OH group because the OH group is wedged, and so there's going to be one line that's dashed. So the carbon, let's highlight it. The carbon we're looking at, the 4 bonds it's making is to this carbon here, this oxygen, and the hydrogen. And so the hydrogen is going to be the 4th priority. Oxygen is going to be first priority. Oxygen is a higher priority than carbon, and carbon is a higher priority than hydrogen. So now it's just between these 2 carbons. So we have to look at what each of those are connected to. This one on the right is connected to a carbon here, and it's connected to a hydrogen right there. So that's C, C, H. Those are the 3 other bonds it's making besides to the yellow carbon. And the one over here on the left is making a bond to this carbon and then 2 hydrogens. So C, H, H. Those are the 3 other bonds that carbon is making besides the one to the yellow stereocenter. So if we look at the 3 things that these carbons are connected to, carbon and carbon, that's the same. Then carbon and hydrogen are the next 2 that we're comparing. So carbon is higher priority than hydrogen, which means that this blue carbon on the left is going to be higher priority, so it's going to be number 2. And the one on, sorry, did I say on the left? On the right. And the one on the left is going to be number 3. Okay? Let's erase everything except for the 1 through 4 marks. Because that's what we're going to use to determine our stereocenter, whether it's R or S. Okay, this is number 2 right here. So we already have, oh, sorry, I erased the hydrogen. We need that. We already have the 4th priority in the back, so that makes it really convenient. We just need to draw an arrow that goes from 1 to 3. 1 to 2 to 3. And since 4 is in the back, we don't need to do any rearranging. If you didn't see my previous video where I explained how to determine R and S, I think at the beginning of this midterm, maybe midterm 2, page 1, I think that was where I explained it. Either that or, yeah, it was midterm 2, page 1 I explained, but I'll re-explain just in case you didn't see. So I basically do it based on the curvature of R and S. So S is shaped like this, you draw it like that, and R is shaped like this. So as you can see, when you start an S, you go around that way, and then form the rest of the S, and when you do an R, you go around this way, and then do the rest of the R. And so if your arrow is going around this way, it's R, because that's what forms the R. And if you're going this way, it's going to be an S, because you can do a squiggly S. Right? So this one, the curve that we drew up there, is going around this way, and that's the start of an S, so this stereocenter is going to be S. Hopefully that makes sense. If you didn't learn it that way, or that way confuses you, there's lots of other ways you can determine R and S based on the curve. Some people just memorize that R is clockwise and S is counterclockwise. This way is better for me though, because I know I would get those confused at some point and switch them. And this way you can't really switch it, you just remember the shape of S and R based on how you write it. But it's up to you if that doesn't work for you. So then that's the answer to the first problem. So moving on to the second one, we're looking at the stereocenter here. And by the way, my trick works if the fourth priority is in the back. If the fourth priority is in the front, then you can do the same thing, but then you just have to do the opposite. Switch it. So if you get the S curve, then it's going to be R. If you get the R curve, it's going to be S. If it's on a plane line, then you have to, or an in-plane line, you have to figure out how to move it either to the front or the back to be able to determine RS. Okay, so now we're looking at the stereocenter here that I'm highlighting in blue. It's connected to, let's get a orange highlighter. It's connected to this carbon here, this carbon here, this carbon here, and it's connected to a hydrogen that's coming out in front next to the carbon and OH, right in front of it. So it's connected to that hydrogen there. Okay? Everything that's connected to is a carbon except for this hydrogen, so the hydrogen is going to be the fourth priority. And then if we look at what each of these carbons are connected to, this one up here is connected to 3 carbons. We're not counting the connection back towards the blue or towards the stereocenter, we're only counting the 3 other ones it's making. So there's the sigma and the pi bond to this methyl or this carbon up here, and then there's also the sigma bond here. So that's 3 carbons. This orange one down here is connected to an oxygen and 2 hydrogens, because there's 2 hydrogens on here, and then there's the oxygen here. Again, we're not counting the blue stereocenter or the bond that's going towards that, we're just counting the 3 other bonds it's making. And then this last one over here is connected to an oxygen, a carbon, and a hydrogen, because there's this oxygen right here for the OH, there's the carbon over here that's part of the ring, and then there's also an implied hydrogen back there. Okay, so let's determine what our priorities are. So the one with oxygen and carbon is going to be our number 1 priority. The one with oxygen still, but no carbon, is going to be our second priority. And the one with only carbons is going to be our third priority. Again, this might throw you off because you're like, oh, there's 2 hydrogens versus there's 3 carbons here, so why wouldn't that be a higher priority? But you just have to look at the biggest priority first. So the biggest priority in all 3 of these carbons is oxygen, and both this one over here and this one have oxygen, 1 oxygen. So then you look at the next priority, which is carbon, and this one has a carbon, this one does not have a carbon. So that's how you look at the priorities. So let's erase everything else except for our numbering to determine what the curvature is. So let's move this one right here. And then let's move that. And then this is number 3 right here. Okay. Now we have 4 in the front, so we need to draw the curve from 1 to 2 to 3, but then we have to do the opposite of the curve. So we draw the curve going from 1 to 2 to 3. You see we went from the 1 bond to the 2 bond right here to the 3rd bond right there. And so that is the curve of an S. But since the 4th group is in the front, right here, the hydrogen is wedged, it's going to be the opposite, so it's going to be an R. Okay. Now it's asking, what is trans to the CH2OH group on the cyclopentane ring? So let's erase all of our work here to make it less confusing. So we already figured out the stereo chemistry. Okay, so let's first identify what is the CH2OH group. So that's going to be where there's a carbon and then an OH. So that's going to be right here, right? Because it says CH2OH group on the cyclopentane ring. So this is the cyclopentane ring, and this is the CH2OH group because there's two hydrogens on that carbon there, and then there's an OH. Okay, so that is the group that's talking about, and it's saying trans to it. So if you'll remember on a ring, it's really limited. You can't rotate within a ring. So all of the substituents are locked in place. So even though trans and cis is usually applied to like alkenes, it can also be applied to rings because there is limited rotation. And so we are looking for something that is opposite of the CH2OH, right? If it was cis, it would be also dashed, like this entire group right here. That is cis to the group that I circled here. Let's just highlight it. That is cis to it, but we're not looking for cis, we're looking for trans. And so since the orange circle group is dashed, we're looking for something that's wedged on the ring. So that would be this OH group, this hydroxyl group is one example. Another example could be the hydrogen, the implied hydrogen that's right here, or the implied hydrogen that's right here, or the, no, yeah, that's it. Just those two implied hydrogens and the OH. And so let's look at what's the options. So the options are the alkene, that's definitely not going to be trans, that's in plane, and the CH2OH group is behind the plane, so that's not trans. The nitrogen, also not, it's cis. That's probably talking about this nitrogen right there. That is cis. The ketone is all the way over here. That's not something that we're even looking at right here because we're looking at the cyclopentane. And the hydroxy, that's the OH group. So that's going to be our answer there for what is trans. Okay, so that's the end of that question. Moving on to milnacipran, however you pronounce that. Okay. So this one's going to be a little bit more difficult. Let's just do it as if we don't know it's going to be more difficult and label the priorities. Okay, so let's look at what this carbon is attached to. So it's attached to, let's just color code the four connecting atoms. There's this one, this one, this one, and then there's a hydrogen coming out in front. Oh no, there's not a hydrogen coming out in front. It's making 4 bonds. The fourth one is going to be that one. That's my bad. There's the wedge group right here for the benzene. So those are the 4 different groups, the ones in purple. So let's identify what each of these are. They're each carbon, right? And so we actually have to look at what each of them are attached to. So this one is attached to 3 carbons because it's attached to this carbon by a sigma bond, also by a pi bond, and then it's attached to that one by a sigma bond. So that one's 3 carbons. This one is oxygen, oxygen, and nitrogen. That already seems like it's going to be a really high priority because it's attached to oxygen twice with the sigma and pi bond, and nitrogen. This one is attached to 2 implied hydrogens, and it's also attached, here, let's erase that, and it's also attached to the other purple group right there. Okay, so that's going to be hydrogen, hydrogen, and carbon. Or I guess we could write carbon, hydrogen, hydrogen. And then lastly, this purple group is attached to this carbon, and the carbon right here, the other purple group, and then a hydrogen, the implied hydrogen right here. So that's going to be CCH. Okay, let's number these priorities because they're all 4 different already, so we don't have to look at the next connection. So this one's going to be number 1 because it's connected to oxygen, and everything else is connected to carbons and hydrogens. And then we're going to look at which one is connected to the most carbons versus the least carbons. So this one right here in the benzene, oh, that's going to be number 2. It's connected to 3 carbons. This one over here is going to be number 3. It's connected to 2 carbons and a hydrogen. And this one over here is going to be number 4. It's connected to 1 carbon and 2 hydrogens. Okay? So let's erase everything else except for our 1 through 4 priorities. Let me just erase that. It's going to be 4. This one's going to be 3. This one's number 1. And this one's number 2. Okay, so what's difficult about this one? So normally we draw an arrow from 1 to 2 to 3, and we want 4th priority to either be in the front or the back. If it's in the back, then we can easily just figure out the curve, and if it's in the front, we can just flip it once we figure out the curve. But in this case, the 4th priority is on an in-plane line, and so a lot of people are tempted to just switch it. Like they do the same thing that they would do if the 4th priority was wedged, and that's not always the case. You can't just like say like, oh, it's going to be the opposite of what it would be if the 4th priority was in the back. You actually have to figure it out, either rotate the molecule so that the 4th priority is in the front or in the back. And so one way, okay, so you can't have a model kit in class, but I decided to use my model kit to prepare for this question because I feel like it's going to be hard to visualize it if you're not used to that. So let's just look at this picture that I have. So this is the way the molecule is already set up. You see that there's a wedged line going to the benzene. There's a dashed line going to the amide group here. And then the CH2 NH2 group over there is behind the cyclopropane. And so that is what we have right here. So we have the methyl group wedged. Here, let's see. We have that wedged. We have the carbon with the double bond to oxygen, the carbonyl, and then the nitrogen here. I didn't draw the 2 methyl groups, or I didn't include those just because that would be a little bit more work. I didn't include the hydrogens either. And then this is the carbon that goes back to the 2 carbons and then the nitrogen. And so, here, let's erase all that. So this one that I'm holding right there, that is our stereo center, right? And the 4th priority is right here. So this is number 4. Let's double check what the other ones were. Number 3 is one that's connected to the C and then NH2. And then 1 is the amide, and then 2 is the benzene. So this is 2. 1 is behind us, and then 3 is right here. Okay? And so I want us to imagine rotating around this bond here. So that basically these 2 will stay where they are, the star 1 and number 3 will stay where they are, and this 4th priority rotates to the back where the amide is in 4th priority. The amide will come out to the front where the benzene is, and then the benzene will rotate down. Okay? This is what I do when I'm figuring out the problems, but I feel like that's kind of hard, so maybe seeing it in the model kit will make it easier. So this is still the stereocenter right here. This is still the star. This is number 3. Like I said, the star and number 3 are still staying where they're at because we're just rotating around this bond between the star and the C. And so now we made it so that the number 1 priority is it's kind of in plane. We kind of want it to be coming out towards us like the benzene was before, but because of the cyclopropane, it's kind of hard to do that. And so it's really on an in-plane line. These are both considered in-plane lines. The benzene is now wedged, and the 4th priority is in the back. This is kind of hard to see. Let's see. So we have, so that's the 4th priority down there. And then we have our, I think I put an extra carbon in there or something. There should have just been 1 carbon attached to the 3rd group here instead of 2. So we have that carbon there, and then the nitrogen, and wait, right? Yeah, that was my bad. And then I didn't include the 2 ethyl groups that are on this, but those basically are also in plane. This is now, these are both kind of dashed, but this is the one that's important that's dashed. This is in plane, this is the double bond O, nitrogen, ethyl, and then coming out right here is the benzene. So, okay, so that's kind of confusing, but hopefully that makes sense for what I mean when I say we want to rotate this basically so that the 4th priority goes into the back. Okay, and then the 2nd priority will come out towards the front, and then the 1st priority will become on an in-plane line. And then as you can see, so if we do this here, okay, so when we rotate it, we are going, let's see, so the orange one and the 3 are going to stay the same, and then our 4th priority is going to the back. This bond is also going to the back, but that's not important for our stereochemistry. So we'll just leave that alone. The benzene is now going to be right here. And then the amide is going to come out in front right here. Nitrogen, and then ethyl. And we still have this, NH2. Okay, so this is our stereocenter right here. This is our 2nd priority, 1st priority, 4th priority, and 3rd priority. So as you can see, when you draw an arrow from 1 to 2 to 3, this is the curve of NR. So that's why the stereocenter is R. Okay, that was probably a bit confusing. It's hard to show with the pictures and drawing on the pictures, but maybe if I erase this, I can just explain it without trying to rotate it. But basically, we go from the benzene here in the front, the amide in the back, this 3rd priority over here on in plane, and this 4th priority in plane. to the fourth priority now in the back, the third priority still in plane, this still in plane, and then we have the first priority, the amide, in plane also, and the benzene still coming out in the front, just from a different angle. And so that's what allows us to draw an arrow from the first priority to the second priority, this benzene, to the third priority with the fourth one in the back. So that curve is the R curve. Okay, hopefully that makes sense. It's kind of hard to explain, but yeah, so that's R. Okay, now looking at this stereocenter, there's another implied hydrogen right here. This time the hydrogen is in the front, so that'll be a lot easier because that's the fourth priority. And let's look at what the four things are that stereocenter is attached to. It's attached to this carbon, that hydrogen that we already claimed is the fourth priority, and that carbon. So let's say what each of these are attached to. This yellow one right here is attached to the carbon here, and then two hydrogens that are implied. I'm not counting the purple carbon. This yellow one that I already drew the arrow to here is attached to the carbon for the benzene. It's attached to the carbon here for the amide, and then it's attached to it's attached back to this other carbon that we just prioritized. So it's attached to carbon, carbon, carbon. This one right here is attached to nitrogen and two hydrogens. And then we have the fourth priority already as the hydrogen. So, let me move that. So nitrogen has a higher priority than carbon, so that's going to be our number one priority since that's the only one with something other than carbon and hydrogen. And then the one with 3 carbons is going to be higher than the one with only 1 carbon. Okay, so let's erase everything else. Let's just recall that number 1. Okay, this is number 1. 2, 3, 4. So we're going to draw a curve from 1 to 2 to 3. And that's going to be the shape of an R. But since the fourth priority hydrogen is in the front, it's going to be the opposite, so it's going to be S. Okay, hopefully that's a little bit easier to understand than the last one. Let's erase all of this so that we can figure out the next part, because that'll be too confusing. So we're looking at the CH2NH2 group on the cyclopropane. What's the CH2NH2 group? That's going to be this one right here, right? Because there's 2 implied hydrogens on that carbon, and then there's the NH2. And so that's the group that we're talking about. And then we're saying, what is cis? So on the same side. And so there is 2 implied hydrogens here. There's the hydrogen in the front and the hydrogen in the back. So the things that are cis to this group is everything that's in the back. So that would be, so the things that are cis to it is this hydrogen that's in the back and this amide group right here. So that's what we're going to say, is it is the amide that is cis because it's on the same side of the cyclopropane as the CH2NH2 group. They're both on the opposite side. They're both dashed. So then the last question of this midterm is asking you to find how many stereocenters are present in this structure. So we're looking for atoms that are attached to 4 different groups. And so let's just go through each atom. It's not going to be this fluorine. It's only attached to, let's just do a red highlighter. It's not going to be this fluorine. It's attached to only one other atom. It can't be any of the carbons in the aromatic ring because they're making less than 4 different bonds. If you're making pi bonds, you can't be a stereocenter. Well, that's not true. You could, if it's like a regular alkene where there's different groups attached to all 4 of the sides, or like if there's, let's see, if it's an alkene where this one is different from this one on both sides, R3, R4, where R1 cannot equal R2 and R3 cannot equal R4. That's another type of stereocenter because we can do E and Z, but that's not the case for any of these because these are all wait. Yeah, I don't think benzenes count for the alkene stereocenters. Yeah, because you can't have the opposite shape for benzene rings. You can't have a cis and trans. You can only have the priorities on the outside. Anyways, so we're just looking for the R and S stereocenters. So this oxygen cannot because it's only making 2 bonds. If we look at this carbon right here, it has this group, the benzene, it has this whole group, it has the oxygen group, and it has a hydrogen. So this is a stereocenter because it's connected to 4 different things. So let's do that one in green. This one is not. It has 2 hydrogen bonds, 2 hydrogen bonds. This one is connected to this whole group. It's connected to this, and a hydrogen. So this is a stereocenter. It has 4 different groups it's attached to. Let's back to green. That's another stereocenter. Okay. This one cannot be because it has a pi bond to oxygen. It's only making 3 bonds to different things. This nitrogen is only making 3 bonds. This carbon here is attached to the nitrogen, it's attached to the benzene, it's attached to this whole thing, and it's attached to a hydrogen, so that's another stereocenter. It has 4 different groups that it's attached to. None of the ones on the benzene can be stereocenters. Along with this oxygen, because it has 2 lone pairs. And then none of the ones on the benzene here can be stereocenters, along with this fluorine. So that's 3 stereocenters. Oh, and also not this oxygen, because it has 2 bonds. So 3 stereocenters. How many stereoisomers? So we could have 2 stereoisomers per stereocenter. We could have the wedge and the dash one because it's not meso. We don't have to consider like repeat ones. And so it's going to be 2 to the power of 3, which is 8 stereoisomers. And that concludes page 6, the last page of midterm 2 for Chem 3A. Thank you for watching.